Hello everybody, so look, we're on part 3 now of our bite-sized chemistry for fuels and heats, not fuels and heats, the octane number and the processes. So we're going to look at two more questions for this one, and that is 2000, starting off with 2010. So let's get started. Part A. Give the systematic names, IUPAC names for three hydrocarbons X, Y, and Z. Okay, let's start. Again, take these as they ought to. So that means you state that X equals, Y equals, and Z equals. That's really, really important that you get that right, because if you're not very clear in an exam, the examiner may not give you the marks. Okay, it's not meant to be a guessing game here. If you're not, you're leaving cert now, guys. Come on. So make sure you put in your X, Y, and Z down here, and put in your naming for them then. Now, if you give them something like this, okay, and you're asked, and again you can see there's brackets there and so forth, it could be hard to determine whether it's an alkane or an alkene. Now, the easiest way for this, for me and him, is to draw this out. Okay, again, you could do it without drawing, but I find that you're going to make less mistakes if you draw it out. Okay, so we have a CH3. I'm just going to do a little side over here. So we have a CH3 grand. That, and then I think we have 5 repeating units of CH2. We do. So I'm going to do 5 CH2s now. So that means 1, 2, 3, 4, 5, and each of those had hydrogens on them. I'm actually not going to bother drawing the hydrogens for this one. And then the very last one, then we have a CH3. So I can see straight away that it's definitely an alkane. Okay, and now I just have to count up I have to count up the number of carbons. So we have 1, 2, 3, 4, 5, 6, 7 carbons there. So we're dealing with heptane. Hept meaning 7. Okay. Again, it wasn't necessary to draw in all the hydrogens there. Okay. We just want to have an idea whether it's an alkane or an alkene. So that's that one. Now we have this guy over here, and lots of students go straight to benzene, but that would be wrong, because benzene, there would have to be a circle inside here, or double bonds present every second one. Okay, so that can't be the case. So what you have to do now is you have to rethink. It's definitely not benzene, but we have a cyclic structure. And if we count up our carbons, there's 6 of them. 1, 2, 3, 4, 5, 6. So we know it's going to be hex. So cyclo, meaning it's in a cyclic shape, hex, and then it's A and E, because there's no double bonds present, cyclohexane. And now Z. Z does have a benzene ring, because you can see that circle in the middle of it, and there's also a methyl group off it, a CH3, so we just call it methylbenzene. Methylbenzene. Okay, so let's move on to part B. B, are we finished with A? Yeah, we are. So, B, compounds X and Z are obtained from the same fraction of oil in the refinery process. Name the fraction in which X and Z occur. So this is X and this is Z here. Z can be tricky enough to figure out, to know that one off. But for X, you should have an idea that heptane is in the naphtha or petrol lineup or fractional distillation. So heptane, and that's for the NAPHTA or petrol. I usually go with naphtha myself. It doesn't matter which one you say, and they're both going to be there in the marking schemes. So that's that. What two properties of compounds are responsible for being found in the same fraction? So it's asking for two properties there, and if they're found in the same fraction, that means they have the same or similar molecular mass. Therefore, they have the same boiling points. So that's our properties there, guys. Okay, we've done this question before, a similar version of this anyhow. Okay, if they're coming from the same fractional distillation, that means they must have the same molecular mass or very similar, and therefore if they have the same molecular mass or similar molecular mass, they're more than likely going to have the same boiling points. That's it. Okay, so that's part B done and dusted. C is asking the first one to be, and I'm not going to write it because again, you know, my writing at this stage now, is to define or what is meant by autoignition. So what is this? Basically, it's a tendency to premature ignition. Okay, so a tendency towards knocking, basically. Okay, it's not good. We don't want that to happen. And then compound Y has an octane number of 83, and therefore has the same octane rating to 8317 as mixture of the two reference hydrocarbons. Okay, name the reference hydrocarbon as the major component of the 8317 reference mixture. Now that was a mouthful really. Okay, there's only two reference hydrocarbons that you need to know. Okay, first one being 2,2,4 trimethyl pentane, and the second one being heptane. Okay, heptane being octane number of 0, and 2,2,4 trimethyl pentane being octane number of 100. And it's asking for name the reference hydrocarbon as a major component. So focus on the major component there, and therefore if it's a major component you could be thinking then it's going to be 2,2,4 trimethyl pentane, which is our answer. That was a bit of a mouthful though. I didn't really like that question myself. Trimethyl pentane. Okay, it's overly confusing. So again, I just read it as a mixture of two reference hydrocarbons. There's only two, and I have to pick out the major one. So the major one being 2,2,4 trimethyl pentane. Next, define heat combustion. We're not going to do that now. That's just a definition. And then for the next one was outline the heat of combustion of X. How can we measure using a bomb calorimeter? We're actually going to do this one because this is the only time I've ever seen this one come up in exams. So let's go for D, and it's our bomb calorimeter. METE or something like that. Okay, close enough. Okay, step 1. I just break them up into steps. And again, don't overcomplicate these. Okay, place a known mass of your substance. Okay, it could be anything. Foods, for that matter, figure out the calories and so forth, into bomb calorimeter. Grand 2. Okay, next one. Okay, burn it completely in excess oxygen. So burn completely, and again has to be using the word excess oxygen to ensure the reaction goes to completion. Excess oxygen, and therefore there'll be max number of products. Part 3. Find the heat produced. Find the heat produced and the heat capacity. So that's the rise in temperature and heat capacity. Now, for those doing physics, there's you'll know yourself now there's actually way more you could be writing there. But for chemistry, like that's all that was required. Okay, you could say you wanted to calculate the heat produced for 1 mole as well if you wanted to. At the very end. Calculate heat produced per mole. There's loads more you could have put in here, guys, if you wanted to. But I just stick to the simple ones there. Place a known mass of substance into a bomb calorimeter. burn it completely in excess oxygen, find the heat produced, that is the rise in temperature and its heat capacity, and then you can calculate the heat produced per mole. Yeah, that's it. So look, we're going to move on now, guys, to our very last one, and that's 2009. And it's not a particularly long one either. So 2009 there is, we're only going to focus on C. So we're reading it there. It says straight chain compounds occur in the kerosene fraction. Upon cracking, you get these molecules here. Enter unbranched alkane molecule. Identify the alkane molecule and state its octane number. So again, we're going back to it for catalytic cracking. We'll state that the product, no, not the product, I should say, the reactant equals the products. So we're starting off with our, let me see, C13H28, 28, I should say. H28, and we're going to get C2H4, I should say, for reading it. C2H4 plus C4H8 plus something else. Okay, straight off we can see both of these are alkenes because both the hydrogens are double the amount of carbons. So what's the story with this? This has to be an alkane. So C and H goes there. Count them up. We have 2 carbons here, 4 here, so that's 6 in total. 6 from 13 will give us our 7. Next we're going to the hydrogens. We have 4 here, 8 here, so that's 12 in total. 12 from 28 there will give us 16, which makes sense because this has to be an alkane. So 7 times 2 is 14, plus 2 gives us the 16 here. So identify this unbranched alkane molecule and state its octane number. Now, identifying it, first off, it's going to be called heptane. And it said unbranched, so therefore heptane has to be the only one we could use for that. And then its octane number is a 0 octane number. Okay, it's one of the reference hydrocarbons, that and 2,2,4-trimethyl pentane. And then it's asking you for draw the structures for 3 of the isomers of C4H8. Okay, so this can be a bit confusing for students sometimes. So let's have a look at that. I'm just going to separate this out now. C4H8. Well, first thing you do, draw out C4H8. So 1, 2, 3, 4. It has to be an alkene, so we'll put in a double bond somewhere. So what you're going to do here is you want to count up all the hydrogens and carbons, and you can see I've made a mistake straight away. This carbon here has to have 4 bonds, and guess it has 1, 2, 3, 4, 5. So I just get rid of one of them there. And it should be fine now. This carbon here has 1, 2, 3, 4. So this is one isomer, grand. So all you have to do is draw the structures, you don't have to name them. Next, let's draw another isomer. Move the double bond. Instead of having a double bond at the very end, put it in the middle. So we have 4 again. Put a double bond here. So put in our hydrogens. You have to be really, really careful with isomerization or making structural isomers, because students make mistakes in this a lot. An awful lot, actually. So look, that's it there. And we have to draw one more. And again, we're trying and figure out what this one could be and trying to think in my head how to do it. I suppose we'll have to put in a methyl group there somewhere. Okay, maybe this one here. The only way you can do is just try it out. So we have a carbon here as a methyl, and then over here we'll have our CH3. I don't even want to go about naming this one, guys. But let's just count out the number of carbons. 1, 2, 3, 4 hydrogens. 3 plus 2 is 5. 5 plus 3 is 8. And we have 8 over here. So that's actually right. Okay, we can leave it at that. That was a very tough one though, to be fair. 2009, yeah, it's going back a while now. It's been a long time since you've got something like this one over here. So guys, look, I hope that helps with the last of our octane number and the processes. Again, there's plenty of definitions in this chapter. You need to know them off. This chapter is guaranteed to come up as your question 6, or at least a full question anyhow, in your state exams. So it's too important to ignore. So look, all the best, and I'll be doing a few more videos on different aspects of this chapter soon enough.